Okay, so our next topic is going to be probability. So lots of this you would have seen at GCSE. This is going to be lots of revision and formalising some of the ideas a bit more. Here's your reference grid for seeing where to get questions on the different topics. Remember, there's no Solomon sheets for statistics, so it's just the Edexcel textbook and the AQA textbook. Okay, first thing to do is go through some definitions and formulas so that we're all at the same starting point. So hopefully you would have seen lots of this at GCSE. So when we're talking about probability, we talk about events. So that means things that are happening. So rolling a die, flipping a coin, picking a card from a pack. They're events. Outcomes are what you could get from that. So getting the heads, getting the tails, rolling a 6, rolling a 5, stuff like that. So if A and B are two events, then A with a little apostrophe, so A dash, is the complement of A. So that means the event of A not happening. And then the NB, that means intersection. So the intersection of A and B, so that means the event of A and B both happening. A union B, so that's the event that A or B happens, and that also includes both happening. A then align B, so that's the event that A happens given that B has already happened. So A given B, that's how you pronounce that one. P brackets A means the probability of A happening. So that's our probability function, the P in the brackets. And two keywords, A and B are mutually exclusive if they can't both happen at the same time. So something like rolling the number 2 and rolling an odd number. Those two events can't happen at the same time. A and B are independent if one happening does not affect the probability of the other happening. So, for example, flipping the tails on the coin doesn't have any impact on what number I roll when I roll a die. And throughout this booklet, you'll meet some of these formulas. Well, the first one you'll hopefully know already. The probability of not A happening is 1 minus the probability of A happening, because probability has to add up to 1. The second one, probability of A or B happening, is the probability of A plus the probability of B, take away the probability of A and B happening. So when we get onto Venn diagrams, you'll be able to see that clearly. Probability of A and B happening is the probability of A happening times the probability of B given that A is happening. And this can be seen when we look at tree diagrams. And mutually exclusive events, well, that means they both can't happen at the same time. So that means probability that A and B is 0. Or equivalently, it means the probability of A or B happening is probability of A plus probability of B. And for independent, remember that means one event doesn't affect the other. So that means probability of A given B is just the same as the probability of A, that B doesn't affect it. Or equivalently, A and B equals probability of A times probability of B. But we'll talk about that when we get onto it. Okay, so the big section of probability Venn diagrams, so we'll spend a lot of time looking at that. So here's some examples of Venn diagrams where there's two events. So A and B are going to be the two events. Now, that first diagram, this diagram here, the bit that's shaded in is the bit that A and B, so the intersection, the middle bit, that's where we put the probability of A and B. If all the circle for A and B are coloured in, that's the event A or B, A union B. So look, that's A, B, and both. So this part of it is just A. This little part of it is just B, and this middle is A and B. On this diagram, the blue bit is everything that's not A, so everything that's outside A is not A. And what we're going to do is we're going to use this Venn diagram here, which I've numbered, so you can't really read it that well actually, but the circle on the left is A, the circle on the right is the event B, and I've numbered the different areas. So I'll do that. So the middle one is 1, the left one is 2, the right section is 3, and the outside section is 4. And what I want you to do is see if you can fill in this table using those numbers. So if I just do the first one with you, and you can try some of the rest yourself. So if I wanted the probability of A, for example, then that would be sections 2 and the section 1. So I would add together those two probabilities because they're both in the A circle. Can you see how many you can fill in yourself? So pause it, see how many you can fill in yourself, and then check. Probability of B, well, that's 1 and 3 together. Probability of A and B, well, that's just the section 1. Probability of A or B, well, that's section 2 plus the section 1 plus section 3. So basically it's everything apart from section 4. Now, how can I write the probability for section 1? Well, that's already been done. That's just probability of A and B. What about section 2? Well, that's the probability of A and not B. So A and B dash. So A and not B. Same for 3. That's the probability of B and not A. And section 4, that's the probability of not A and not B. If I wanted the probability of not A, well, that's everything that's not A. So that's section 3 and section 4. For not B, that's everything that's not B. So that's section 2 and 4. If I want A given B, well, given that B's happened, that means I'm only looking at the B circle. So if I just shade in this, so this is my only area I'm looking at now. So this, given that, are always kind of fractions. So on the bottom of my fraction, I'm just looking at section B. So that's going to be 1 and 3. And what's the probability that A happens, given that that's happened? Well, out of those numbers 1 and 3, the one that includes A is 1. So it's 1 over 1 plus 3. And the probability of B, given that A has happened, well, given that A has happened, that means I'm looking at this circle now. So on the bottom of the fraction, I'd have 1 and 2. And out of those, what's the probability that B happens? Well, that's just 1. So it would be that probability there. So 1, 2, 3, and 4, they would represent probabilities. And I would just sub those into those little formulas. Okay, let's have a go at looking at that formula now. So looking at the Venn diagram, it's quite easy to see that the formula for probability of A or B is the probability of A plus the probability of B, take away the probability of A and B. Now you think of that, that's because if I have circle A and I add on circle B, then you can see I've included the middle bit twice. So I need to subtract this middle bit, which is the A and B. So that's where that formula comes from. However, if you get really good at drawing diagrams, you can kind of do this as like a logical puzzle instead of actually using formulas. Yeah, if they're mutually exclusive, that means there won't be any intersection. So the probability of A or B is just the probability of A plus the probability of B. That's what this last bit's in here. However, just looking at the Venn diagram, it's quite tricky to spot easily if events are independent. It's easy to spot if they're mutually exclusive, but it's not obvious if they're independent. Okay, let's have a go at an example. So chocolate is selected randomly from a box, so I don't really care about that. The probability of it containing nuts is 1/4, so I'm going to highlight that. The probability of it containing caramel is 1/3, so I'll highlight that. The probability of it containing both nuts and caramel is 1/6. What's the probability of a randomly chosen chocolate containing either nuts, caramel, or both? So let's have a go at drawing a Venn diagram for this. So 2 circles. So have a nuts and caramel. If we can, we always try and fill in the middle first. So in the question, does it tell us the probability of both happening? Yeah, it does. It says that's 1/6. Now it says for nuts, it's 1/4. So that means the bit here where I'm going to put a green little dot has to make this circle add up to 1/4. So where I put my green dot, I'm going to do 1/4, take away the 1/6, which is going to be there. So if you use a calculator to do that, or just do it in your head, you should get, if I can type in my calculator properly, 1/12. And for caramel, the probability is 1/3. So using the same logic, this circle is 1/3. So to get this, whether I put my blue dot, I'm going to do 1/3, take away the 6 that's already there, which is going to give me 1/6. And then to get the outside, where I'm put, let's use red, where I'm putting my red dot, everything has to add up to 1. So to get that red dot, I'm going to do 1 minus 1/12 minus 1/6 minus 1/6. Which gives me 7/12. Because everything has to add up to 1, and the probability always adds up to 1. Okay, so now we can have a go at answering the question. So once, what was the probability of it containing nuts or caramel or both? So that's asking for the probability of nuts or caramel, so that everything that's inside the 2 circles, so that's 1/12 plus 1/6 plus 1/6. So 1/12 plus 1/6 plus 1/6, which gives me 5/12. So you could have got that a couple of different ways. If I knew the outside was 7/12, I could have took that away from 1, which would have given me 5/12. I could have used the formula up here and do probability of nuts, which was 1/4, plus probability of caramel, which is 1/3, take with the probability of both, which was 6, and that should give me the same answer. So I could have used the formula, and done probability of nuts plus probability of caramel minus probability of nuts and caramel. So that was 1/4, add 1/3, minus 6, which again gives me 5/12. However, I always think it's easier to draw a good diagram. Just like in mechanics, you would draw a diagram. In statistics, drawing a good diagram helps, so you don't have to worry about these formulas. Okay, so let's look at a little bit of conditional probability. So just like I did a few slides ago, if I just jump straight to this diagram here, you can do the reading yourself. This probability here, A given B, well, first of all, I would just restrict my diagram just to B, because I know that B's happened, so I would only look at this part of the Venn diagram. So on my fraction, to get the probability, I would just put B on the bottom. And the bit that includes the A would be the middle. So out of those, I want this bit here, the middle. So that's the probability of A and B. So that's where this formula here comes from. So the bit that's given goes in the bottom of the fraction, and both goes in the top. Now, you're given in the formula booklet it written in this form. To get it in the fraction form, just divide to get the given bit as the subject. So you're given this formula, although this formula is quite logical to think about. So most stuff is conditional probability. So that's when one thing does affect another one. So in an example above, it's talking about some people owning a car and the probability of them passing a driving test. But obviously, if you own a car yourself, you're likely to do more practice in your own car, so you might be more likely to pass a driving test. So that will be a conditional probability because they're not independent. Okay, so let's have a go at doing an example. So A and B are two events such that the probability of A is 0.55, probability of B is 0.4, and probability of A and B is 0.15. Draw a Venn diagram showing the probabilities for events A and B. So if I draw a Venn diagram, so here's A, here's B. Again, we try and put the middle in if we can, and we know the middle, A and B, is 0.15. Now, I know that the A circle should add up to 0.55. So to get this red dot here, I want to do 0.55, take away the bit that's already there, the 0.15. So I'm going to get 0.4. I know that B adds up to 0.4. So to get this blue dot, I'm going to do 0.4 minus 0.15, which gives me 0.25. And to get the outside, I know that everything should add up to 1. So I'm going to do 1, take away 0.4, take away 0.15, take away 0.25, which is going to give me 0.2 on the outside. So I've got all my probabilities that I potentially need. So now, working on probabilities is going to be really nice, really quick. So if I'm doing probability of A given B, then B already happened, so I'm only looking at the B circle. So I'll highlight this bit in green. So I'm only looking at that. So my total I'm looking at is 0.4. It's those two things together. And I'm going to write it as those two things added together. So hopefully you can clearly see what's happening. Now, out of those two things, which one includes the probability that A happens? Well, it's the 0.15. So to work out that probability, I'm just going to type that in my calculator. So 0.15 over 0.4, and that gives me, as a decimal, 0.375, or as a fraction, 3/8. Yeah, so when you have conditional probabilities like this, what you're doing is, instead of having the probability out of 1, you're restricting it, so you're having probability out of the second bit. So the second bit goes in the bottom. And you're only looking for the bits of those that include the first bit. And in this case, that was just this 0.15. That's the only bit that included the A look. Okay, so the second one says, find the probability of B given that A or B has happened. So straight away, I'm going to have a fraction, and I'm going to look at what's the probability that A or B's happened, which bits of the circles. And this is going to be quite hard because I've already colored some of them in. Can I rub out just the highlight? Let's see if I can do that. No, it's going to rub out the numbers as well. Okay, so I'm going to highlight over it. A or B, so that's all of A, all of B. So I'm looking at those three numbers there. So I'm restricting my area I'm looking at to 0.4, 0.15, and 0.25. So out of those, which ones have the B? Which ones are the probability of B happening? And it's the 0.15 and it's the 0.25. So I'm going to type that in my calculator. And I get 0.5, or again as a fraction, that's a half. So again, we're looking at A or B happening, and we put that on the bottom. So that was all the things inside the circle. Then we say out of those, which ones are where B happens, and it was the 0.15 because that was the middle, and 0.25 because that was just B happening, and they go on the top. And the last one says find the probability that A doesn't happen given that B doesn't happen. Okay, so what colour can I try and do this one? Let's do this. Let's use a different colour. Let's use pink. Okay, so I'm going to highlight the bit that I'm looking at, so I'm restricting it to where B hasn't happened. So that's everything that's not inside the B circle. So that's all this bit in pink. So the bottom of the fraction are going to be these two things here. So 0.4 and 0.2. And out of those two, I'm looking for what's the probability that A doesn't happen, and that's just the 0.2 bit. So again, we type that in a calculator, work it out, and we get a third. So just to go through that again, we looked at the bit where B doesn't happen. So that was the outside of the B circle. So that was 0.4 and then 0.2. Then we said out of those numbers, out of those probabilities, which ones are the ones where A doesn't happen. Now the 0.4 was inside the A circle and the 0.2 wasn't. So that goes on the top of the fraction as well. Okay, let's have a go at another one. So the probability that a randomly chosen resident of a city in Japan is a millionaire is 1 over 10,000. So millionaire is 1 over 10,000. The probability that a randomly chosen resident lives in a mansion is 1 over 30,000. Only 1 in 40,000 are millionaires who live in mansions. What is the probability of a randomly chosen individual being a millionaire given that they live in a mansion? Okay, well, let's draw a Venn diagram for this. And annoyingly, they use millionaire and mansion, so I can't use M and M. So I'm going to use pound symbol for millionaire and M for mansion. So remember, we want to try and see if we've got the probability of both happening, and we do, because it says only 1 in 40,000 are millionaires who live in mansions. So that's 1 over 40,000 is in the middle to get this bit here, which I'm calling red. So that's the millionaires. So I know that altogether there should be 1 over 10,000 millionaires. Well, the probability of being a millionaire is 1 over 10,000. So I'm going to take away what's already there. I'm going to take away the 1 over 40,000. And I'm going to work that out, which gives me 3 over 40,000. Same thing for the mansion. So I know that there should be 1 over 30,000 for mansion altogether. So I'm going to take away the 1 over 40,000, which is there. And that's going to give me 1 over 120,000. Then to get the outside bit, I'm going to take everything away from 1. So 1, take away that, take away that, take away that. Which is going to give me 119,987 over 120,000. So the probability that people don't live in a mansion and aren't a millionaire is nearly 1, which is what you'd expect. So we want, let's read the question, what it wants at the end. What's the probability of a randomly chosen individual being a millionaire given that they live in a mansion? So when I'm doing my probability, I'm putting a given that after my line. So given that they live in a mansion, what's the probability that they're a millionaire? So that's the probability I'm trying to work out. So it's the given that. So I'm given that they live in a mansion. So if I go to my Venn diagram, I'm only looking at this mansion circle here. So straight away at the bottom of the fraction, I'm going to have what I had, my fractions on fractions. And I know what these two add together because it tells me in the question that a mansion is 1 over 30,000. I'm just writing these as 2 fractions to really emphasize that it's one of these numbers that's going to be on the top. And out of these 2 numbers, so out of that circle, the yellow circle I'm looking at, what includes the millionaires, it's the 1 over 40,000. Yeah, then I would just type on my calculator to work it out, or I could just times top and bottom by 120,000. So I get 3 over 3 add 1. So I get 3/4. So given that someone lives in the mansion, the probability that they're a millionaire is 3/4, so 75%. And again, does that make sense? Well, yes, because if you live in a mansion, the odds are you want to have lots of money, aren't you? So again, go through that one more time. So I'm given that to live in a mansion. So I'm looking for which sections live in a mansion. So that's these 2 numbers here. So they go on the bottom. And out of those 2 numbers, which ones are millionaires? Well, that's only that one there. I'm ignoring the 3 over 40,000 because that's not part of the mansion section. And then we just work that out. So just type in your calculator, or just times top and bottom by 120,000 to make them into nicer numbers. Okay, and here's an exam question. However, there's a typo, so it should say that 100 people are asked what type of wine they like. So just add in, so 100 people asked. So it says 99 like wine A, 93 like wine B, 96 like wine C, 92 like A and B, 91 like B and C, 93 like A and C, and 90 like all 3 wines. So we've got a high proportion of people who like wine. So draw an appropriate diagram to represent this data. So the best kind of diagram to draw when we've got lots of different options is a Venn diagram. So I'm going to have wine A, wine B, and wine C. So they're overlapping. So I've got lots of different sections. So as always, I'm going to try and fill in the middle. So just to tell me anywhere who likes all 3 wines, and it says 90. So I'm going to put 90 in the middle. Now in this bit here, I'm putting my red dot now. That's the people that like A and B. So if I find that number, that's 92. However, I've already got 90 people in there, so I just need 2 more. Where I'm putting this dot, that's B and C. That's where B and C overlap. So I find B and C, and that's 91. However, I've already got 90 in there, so I'm just going to put 1 more person. So that 1 person likes B, C, but not A. Then I'm looking here, so that's A and C. So 93 people like A and C. Well, 90 people like A, C, and B. So that means 3 people like A, C, but not B. Okay, so now I can work outwards again. So I can look for A. So A, it tells me that 96 people like A. However, I've already got 95 people in A already. So that means I need 1 more person. Now I can do B. 93 people like B, but I've already got 92, 93. I've already got 93. So that's a 0 there. So that means no one just like wine B. If they like wine B, they're automatically like A or C. And for C, 96 people like wine C. Well, I've already got in circle C 93 and 1 to 94. So I need 2 more to make 96. And to get the outside, I'm going to do 100 minus those numbers. So 90, take away 1, take away 3, take away 2, take away 1, take away 0, take away 2. So I'm just starting in the middle and working outwards. So there's one person. So one person likes none of the wine. I don't know where to ask these 100 people. Okay, so given the diagram, find the probability that randomly selected person from the survey likes none of the wines. So I could write that as, if I zoom in, so I've got the space to write it, I could write that using notation as probability that they don't like A, and they don't like B, and they don't like C. So that was the outside, so that was only one person out of 100 people. Okay, find the probability that they like A, but not B. So that's the probability that they like A and not B. Well, if I look at the A circle, I've got the numbers 1, 2, 19, 3. Which of those don't include B? Well, the 290 are in the B circle as well. So that's the 1 and the 3 that aren't. So that's 1 and 3 makes 4. So there's 4 people out of 100, which I could simplify to 1 over 25. Next one. What's the probability that they like any wine in the survey except C? So that means we want the probability that they don't like C, however, they do like A or B. So they like some kind of wine, just not C. So that means we want someone that's in the circle, in one of the circles, but not the C circle. So if I ignore the C circle and look at just the others, I've got a 1, 2, and a 0. So that's 3 people. So 3 people like wine apart from C. Okay, E, exactly 2 of the 3 kinds of wine. What's the probability to like exactly 2? Well, A and B, 2 people like just those 2. 3 people like just A and C. 1 person likes just B and C. So I'm looking, I'll highlight these in to make it a bit easier. I'm looking at these 3 numbers here. The 1, 2, and 3. They're where they're just like 2 wines, exactly 2 wines. The 90 in the middle likes all 3, so I'm not including that one. So if I add those together, I get 6. So I get 6 out of 100, which I can simplify to 3 out of 50. Okay, the next bit, the final bit, it's got the keyword here, given that. Given that a person from the survey likes wine A. So I'm given that they like wine A. So straight away, a probability that they like A. Find the probability that the person likes wine C. So that means I'm finding the probability that they like C, given that they already like A. So if I go on my diagram, I'm only looking at the A circle. So if I do that one in green, because I've already used yellow, so I'm looking at the A circle. So they like A, so they're these 96 people here. So on the bottom of my fraction straight away, I'm going to have 96, but I'm going to write it as the 90 plus 2 plus 3 plus 1. So out of those people who also like C, well, these 3 people do here. Sorry, that should be in a highlighter. These 3 people do here, and these 90 people do here. So the 90 plus the 3, so 93 people. So I've got 93 people out of 96, and then I'm sure that simplifies. Just, 31 over 32. So given that they like wine A, there's nearly 100% chance that they also like wine C, sorry. Okay, here's another one. So we're given that the probability of A is a half, B is a quarter, and there's a little not there, so not A or B is 5/12. And we want to find out some probabilities. So again, let's draw a Venn diagram. Okay, so A and B. So probability of A is a half. So this whole circle for A is a half. The whole circle for B is a quarter. And this third one here, not A or C, not A or B, is 5/12. So this probability here is actually the same thing as not A and not C, not B. Why am I keep calling B C's? Because it says we don't want A or B, so that's the same thing as not having A and not having B. So far, the only probability I can put on there is 5/12. Okay, well, if that's 5/12, then let's try and use the fact that everything adds up to 1. So the middle is the bit I would try and fill in first, but I don't know the middle, so I'm just going to call that x. So therefore, if that's x, A would be a half minus x, and B would be a quarter minus x. And I know that everything would add up to 1, so I know that a half minus x, add x, add a quarter minus x, add 5/12 would add up to 1. Okay, well, if I simplify that, so half, add a quarter, add 5/12, gives me 7/6. Minus x plus x minus x gives me just minus x. That would equal 1. Well, if I just cheat here, if I think of 1 as 6/6, then very quickly I get that x must be 1/6. Because 7/6, I need to take away 1/6 to get 6/6. So I've got the numbers now. So I can fill them in my diagram. So x was 1/6. A half, take away 1/6 is a third. And a quarter, take away 1/6 is 1/12. So I've got all the numbers I need now. So now the question's going to be nice and easy. So the first one's asking for probability of A and B. Well, we worked it out. That was the middle. That was 1/6. And B, hence find probability A given B. So again, B's happened. So I'm only looking at the B circle. So let's highlight the B circle. So my probabilities I want are 1/6 and 1/12, which I know adds up to a quarter. It tells me that in the question. Remember, I'm just writing them separately so that you can see my options for the top. So out of those two, which ones give me the probability of A happening? And that's 1/6. So I can type down my calculator, or I can times top and bottom by 12 to get 2/2 add 1, so 2/3. So given that B's happened, there's a 2/3 chance that A happens. So the trick we did there is, if I don't know the middle, call the middle x. And make an equation, use the fact that everything adds up to 1, so that you can then solve it. Okay, another example. In a class of 32 students, 19 have a bicycle, 21 have a mobile phone, and 16 have a laptop computer. 11 have both a bike and a phone, 12 have both a phone and a laptop, and 6 have both a bike and a laptop, and 2 have none of these objects. So it's straight away, let's draw a Venn diagram. So we have a bike, we have a mobile phone, and we have a laptop. Actually, I'm going to call the mobile phone P, because they've changed the word to phone later on, just so I'm not confused. Okay, so I know there's 32 students all together. So I'm just going to write in the corner outside 32 to remind me that everything should add up to 32, because I can write numbers inside as probabilities, or I could just write them as numbers as long as I know that the total isn't 1 anymore. So I don't have how many people there are all. I'll like have all 3. So I'm just going to put the middle X. Actually, let's use a different color. Choose red. So I put the middle X, and then it says 19 students have a bike. Actually, so let's look for where it's talking about bike and phone. So 11 have a bike and phone. So that bit I'm going to put 11 minus X. It says 12 have a phone and a laptop. So that's here. So that's where the P and the L intersect. So I'm going to write that as 12 minus X. It says 6 have a bike and a laptop. So that's this bit here. So I'm going to write that as 6 minus X. I know that there's 2 people that have none, so that can go on the outside. It says 19 people have a bicycle. So I know that this circle here, the bicycle, should add up to 19. Well, if I look at what I've got already, I've got 11 minus X, 6 minus X, so that's 17 minus 2X, plus X, so that's 17 minus 1X. So to get to 19, I need 2 plus X. So that now adds up to 19. It says 21 have a mobile phone. So if I look at the phone, I've got 11, take away X, 12, take away X, and X. So altogether, I've got 23, take away 2X. So if I add X to that, I've got 23, take away 1X. And that needs to add up to 21. So to get from 23 minus X to 21, I need to minus 2 and plus an X. And for the laptop, it's 16. In the laptop, I've already got 6 and 12. So I've got 18 minus 2X plus 1X, so 18 minus X. And I want to get to 16, so I need to take away 2 plus X, the same as before. And now I know that everything should add up to 32. So let's make an equation. So I've got X. If I work from the middle outwards, add 11 minus X, add 6 minus X, add 12 minus X, add, keep working outwards, so I've got 2 plus X, add minus 2 plus X, add another minus 2 plus X, add that number 2, that should add up to 32. So let's simplify this. So that X and that minus X can cancel, that X and that minus X can cancel, that X and that minus X can cancel. So I'm just left with 1X. Now I've got 11, add 6, add 12, so that gives me 17, 29. Add another 2, gives me 31. Take away 2 gives me 29. Take away another 2 gives me 27. So X add 27. I don't know if I added that extra 2. I don't think I have. Let's double check that again. 11 add 6 is 17. Add 12 gives me 29. Add 2 is 31. Take away 2 is 29. Take away 2, 27. Add that 2 is 29. So sorry, X add 29 must equal 32. So therefore, X must equal 3. So I can answer that first bit. How many have a bike, a phone, and a laptop? Well, there's 3. So I can now fill in all those numbers. So if X is 3, 11 minus 3 is 8. 6 minus 3 is 3. 2 plus 3 is 5. Minus 2 plus 3 is 1. 12 minus 3 is 9. Minus 2 plus 3 is 1. So I've got all the actual numbers now. Part B, what is the probability that a randomly chosen student from the class has all 3 items, given that they have at least 2 of the items. So we want probability of all 3, given that at least 2. Straight around the fraction. So which sections have at least 2? Well, these have at least 2, these have at least 2, these have at least 2, and these have at least 2. So these 4 numbers, I'm going to put those 4 numbers in the bottom. So 8, add 3, add 3, add 9. So out of those numbers, which ones have all 3? Well, that's just the middle bit. So on the top of that fraction, I'm going to have just that 3. So if we work that out, we get 3 over, is that going to be 15, 23? So 3 over 23. Yeah, so the same trick, just a bit longer this time. Again, make the middle bit equal to your x, so that you can write everything in terms of x, make an equation, and solve for x. Okay, let's talk a little bit about independence now. So if A and B are independent, then that means A given B is just the probability of A. B doesn't affect it. And equally, B given A is just B. So using the formula for intersection, so I know we haven't talked about this too much, we can deduce very quickly that the probability of A and B is probability of A times probability of B. So remember, like I said, you're given the formula for intersection, you're given that probability of A and B is the probability of A times the probability of B given A. That's in your formula booklet, and we'll talk about that more with tree diagrams. However, if they're independent, then the second probability here is just probability of B. So therefore, if it's independent, then the probability of A and B happening is just the product of them happening separately. Yes, that's a useful thing to know. So let's have a look at an example where we're going to use this. So given that probability of A is 3, probability of B is 4, and probability of A and B is 0.25, we're going to explain why events A and B are not independent. So let's do that first of all. Well, if independent, then probability of A and B is equal to probability of A times probability of B. But if we look at that, the left-hand side, probability of A and B, the question tells us is 0.25. The probability of A is 0.3. Probability of B is 0.4. If I times those together, I get 0.12, and that doesn't equal 0.25. So it's not independent because this formula doesn't work. Yeah, so if you have to check if something's independent or check if show that it's not independent, just use that formula and see if it works or if it doesn't work. Okay, let's carry on reading the question. Given that the probability of C is 0.2 and that events A and C are mutually exclusive, so that means they can't happen at the same time, and that events B and C are independent now, so there's lots going on in this question. Draw a Venn diagram to illustrate events A, B, and C, showing their probability for each section. Okay, well, we know that A and C are mutually exclusive. So that means my A and C circles don't touch. However, the B circle touches. I know that B and C are independent. So that means the probability of B and C is equal to the probability of B times the probability of C, because they're independent. So I can use that formula to get the probability of B and C, because I haven't got that. B was 0.4, C was 0.2, so the probability of B and C is 0.08. Okay, so let's see if we can fill in some middles. So I've just worked out B and C. So that's 0.08. Let's make that look more like an 8 so I don't get confused. Do I have A and B? Yeah, I do. That's 0.25. Well, A should be 0.3. I've already got 0.25, so that's 0.05 left. B should be 0.4, but I've already got 0.25 and 0.08, so that's 0.33 so far. So I need 0.07. C, it told me that was 0.2. I've already got 0.08, so therefore I need 0.12. And to get the outside, I'm just going to do 1, take away all those numbers. So if you just type that in your calculator, I get 0.43. So I've got all the probabilities I need in that diagram. So the key to help me doing that was using the fact B and C were independent, which means I can use that formula there. And it says, find the probability that A and B, A and not B, or C happens. Well, let's highlight the bits I want. So I want A and not B. So that's this bit. A and not B is that bit. Or I want C happening, which is this bit. So that probability is just those added together. So the probability of A and not B or C is 0.05, add 0.08, add 0.12, which gives me 0.25. Okay, so you might want to do a bit of independent practice now. Okay, so far we looked at Venn diagrams. They're really useful. Another useful diagram that we can use for conditional probabilities is two-way tables. So let's just do a quick example. So these data show the arrival time of a random sample of 100 letters. I'm going to highlight the number 100, as well as whether they were posted first class or second class. Okay, well, two-way tables are very useful if I have the totals. So first class, altogether, there were 80. For second class, there's 20. For next day, it was 76. And for later, it was 24. So I've got all the totals as well, and they should add to 100, which they do. So on the basis of these data, find the probability of first class and next day. Well, first class and next day. Let's do this in red. First class and next day. Well, there were 64 letters out of 100, which can be simplified down to 16 over 25. B, find the probability that it was delivered next day, given that it was first class. Well, first class, we're looking at this row. Again, that should be highlighted. So we're looking at AD altogether. So AD is going to go on the bottom. But I'm going to write AD as 64 and 16. So out of those, which ones were next day? Well, it was 64. So it's 64 out of 80, which gives us 0.8 or 4 over 5. And C, find the probability it was first class, given that it arrived next day. So I'm going to do this one in green. So this was my next day, so there's 76 altogether. But I'm going to write that 76 as 64 and 12. So out of those, which ones were first class? It was 64. So it's 64 out of 76, which as a fraction is 16 over 19. Yeah, so two-way tables are nice and quick when you're talking about conditional probability. So here's an exam question using two-way tables. So a house in the estate consists of 320 houses, 120 detached and 200 semi-detached. The numbers of children living in these houses are shown in the table below. So I'm not going to highlight those numbers because they're already all in the table. So a house on the estate is selected at random. So we have these different events. D is the event the house is detached. R is the event no children. S is one child. And T is two children. Then two of the events that are mutually exclusive. So two that can't happen at the same time. Well, R and S are mutually exclusive. So you can't have no children and one child. R and S. You could have R and T, or you could have S and T. Yeah, because those are the pairs that can't happen at the same time. Determine whether the events D and R are independent. Justify your answer. Well, if they're independent, remember that formula would work. So if independent, we would have the probability that D and R equals probability of D times probability of R. So let's check that. Well, D and R, so detached and no children. So detached and no children is 24 out of 320. Probability detached is 120 over 320. Sorry, I shouldn't have been equals there. I'm checking if this works. Yes, I'm checking. So I'll put a question mark there. I'm checking if that works. And probability of no children, well, that's 64 out of the total 320. So if I times our right hand side together, I get 3 over 40. And if I simplify the left hand side, I get 3 over 40. So it works, so therefore independent. So whether the house is detached or not doesn't affect if no children live there. Okay, the next bit, define in the context of the question the event D dash or T. So D dash, well, if it's not detached, and this question must be semi-detached, because houses are either detached or semi-detached in this estate. And T means two children live in the house. So in the context of this question, we're not D, so we're looking at we live in a semi-detached house, or we have T was two children, or two children live in the house. Or you could have both. You could have a semi-detached and two children living in the house. So the word or in English could also mean both. And the second one, D and R or C. So R meant one, no child. S meant one child. So R or C means none or one. So we could call that at most one. That might be a good way of saying it. At most one child. And D means detached. That means detached and at most one child. Okay, and the last diagram that's helpful are tree diagram. So you've seen GCSE. So this is an example just on the screen now, where first of all we look at what options we have for main course. So you can see we've got a burger, lasagna, or pie, the probabilities of what's happening. And then the second option is if the person wants chips, I guess. So you can see that probabilities here, if I hide them, are different for each branch. So for some reason, if you have lasagna, you don't have chips. don't know why not. So that means that they're not independent. So the chips in your main course are not independent. Whether you have chips depends on your main course. So this would be a conditional probability. So this 7 over 8 here, the first one I highlighted, isn't the probability of chips. This thing here is the probability of chips given that we have a burger. This probability here is the probability of chips given we have lasagna. This probability here is probability of chips given that we have pie. Okay, we'll talk about how we get the probability of chips in a second. Now, you know from GCSE that if you want what's the probability that someone has burger and chips, then if I go along the branches, I would just times these together. And what's normally useful is if you just do that straight away in the question without being prompted to do it, so you're ready to work stuff out. So if we just work out those combinations, so I times them together, I would get 7 over 20. I would get 1 over 20. I would get 0. I would get a half. I get 1 over 50. And I would get 4 over 50. I'm just seeing if I can simplify that. I obviously can. 2 over 25. Okay, so I've got all those probabilities. So the 7 over 20 is burger and chips. 1 over 20 is burger and not chips. 0 is lasagna and chips. Half is lasagna and not chips. 1 over 50 is pie and chips. And 2 over 25 is pie and no chips. Okay, so here's the formula you're given, remember? So if I want a probability of something and something happening, so A and B, I first of all need to go down one of the branches, so B, and then I will go down the branch A, but given that B's happened, so it will be A given B. And if I wanted to work out what's the probability of chips happening overall, then I have to add all the options that have chips in. So this one has chips, this one has chips, and this one has chips. Not that last one, what am I doing? This one has chips. So I'd have 7 over 20. I would have 0, and I have 1 over 50. So I could add those together, and I would get 35 over 100 and 200, so 37 over 100. That's the probability that someone has chips. Yeah, so if you want the probability of the second branch, what you don't do, you don't just add up these probabilities straight away. Like you're going to see, you're going to get them bigger than 1. You add up the end probabilities. These ands at the end are the ones that put the Venn diagram. Let's look at this in more detail. So just like we did with our Venn diagram, I've got a tree diagram. So the first branch is A and not A. The second branch is B and not B. But notice at the first branch, look, this is B given A has happened. This is not B given A has happened. This is B given A hasn't happened. And this is not B given A hasn't happened. And the numbers we are right at the end are the numbers I would times them together. So I'm going to call this one 1, 2, 3, and 4. So maybe see how much of this you can fill in yourself. So if I wanted the probability of A, well, it would just be that probability here, or it should also be the numbers 1 and 2 added together, or the probabilities 1 and 2 added together. If I wanted B, then it will be the ones that include B, so it's these options, so that would be 1 and 3. If I wanted A and B, that would just be the number 1. If I wanted A or B, then that's anything that has an A or B in it. So the first branch does, the second branch does, because they've both got A in. The third branch does because I have the B in, but the fourth one does it. So it's 1 add 2 add 3. Option 1, well, I can write that as that was A and B. Option 2 was A and not B. Option 3 was not A and B. And option 4 was not A and not B. If I don't want A, then that would just be that probability there, which would also be probabilities 3 and 4. Not B would be these probabilities here, which would be 2 and 4. If I wanted A given B's happened, well, I would put the probability that B's happen on the bottom. So the B ones were 1 and 2, 1 and 3, sorry. And out of those two, which ones had A? That was 1. And if I wanted B given A, well, it's just that probability there. But that's the same thing as doing, well, A's happening is 1 and 2. And out of those two, it's just 1. Now, if you compare this to when we did the same thing for Venn diagram, you should see we get the same results. Okay, let's have a go doing an exam question, an example now. So Layla has a test at the end of the week for history. If she revises for a particular test, Layla estimates there's an 80% chance she will pass. So if she revises, there's an 80% chance she will pass. However, if she does not revise, she estimates there's only a 30% chance of passing. The probability that Layla revises for any particular test is 3/4. What proportion of her history tests should Layla expect to pass? Well, let's look at what probabilities we're given. This 80% there is the probability of her passing. Probability of her passing, given that she's revised, was 80%. So I'm going to write that's 0.8. And the 30% was the probability of her passing if she didn't revise, given that she didn't revise. That was 30%. So I'm going to write that as 0.3. So if I've got given that in the question, it's normally best to draw a tree diagram instead of a Venn or two-way table. And to decide what branch goes first, look at the bit that's given. So I'm given that revision has happened or not happened. So on my tree diagram, I'm going to have revision and not revision. So the probability she revises was 3/4, it said. So therefore not revised must be 1/4, because these two branches have to add up to 1. If she revised, what's the probability that she passes? And what's the probability she doesn't pass? What's the probability she passes if she doesn't revise? What's the probability she doesn't pass? So if she revises, the probability she passes was 0.8. So I'm going to write that as 4/5. So the probability that she doesn't pass is 1/5. If she doesn't revise, the probability she passes was 0.3. So I'm going to write that as 3/10. So therefore, the probability she doesn't pass is 7/10. Because again, those branches have to add up to 1. Each set of branches need to be add up to 1. So the question says, I didn't actually read what the question wants. What proportion of her history tests should Layla expect to pass? Well, remember what I said about it's a good habit to work out straight away the probabilities of things happening. So revising and passing. So if I times these together, I will get 3/4 times 4/5 gives me 3/5. So that's the probability that she revises and passes. 3/4 times 1/5 gives me 3/20. That's the probability that she revises but doesn't pass. 1/4 times 3/10 gives me 3/40. So that's the probability that she doesn't revise but passes. And 1/4 times 7/10 is 7/40, and that's the probability that she doesn't revise and doesn't pass. And you can always double check by making sure those 4 probabilities add up to 1. So those 4 probabilities at the end should always add up to 1. Let me just double check that to make sure I haven't done something silly. That's what happens when you have 2 weeks off maths. You do lots of silly stuff. Yep, it all adds up to 1. And we're working out what proportion of a history test should she expect to pass. Well, this one, if I get the highlighter, this one involved passing, so I want this number. And this one involved passing, so I want this number. So the probability that she passes, because proportion just means probability, what fraction, percentage, whatever you want to think of it as, is 3/5 as 3/40. And if I work that out, it gives me 27/40. So that's what proportion she should expect to pass. Out of 40 tests, we'd expect her to pass 27. Some of them would come from not revising. Some of them will come from, well, the majority, hopefully, would come from revising. Yeah, you can see actually 3 of those would come from not revising, 24 of those would come from revising. So that's, again, important to see that revision matters. Okay, next one. So if it is raining in the morning, there's a 90% chance I will bring my umbrella. Well, why is it 90? Why is it not 100%? So if it's raining, 90% chance bring an umbrella. If it's not raining, there's a 1/5 chance of taking my umbrella. On any given morning, the probability of rain is 0.1. So again, let's write out what those probabilities are. So 90% chance is the probability that I bring an umbrella, given that it's raining. So that was my 90%. And the 1/5 was the probability that I bring the umbrella, given that it's not raining. So again, I've got conditional probabilities. That makes sense to do a tree diagram, and on the tree have the first branch as rain or not rain. And it says the probability that it rains is 0.1, so not rain must be 0.9. Then if it rains, the probability of bringing an umbrella or not, well, you should take an umbrella, so it should be probability 1, but it's 90%, so we'll write that as 0.9. So not bringing an umbrella probably would be 0.1. If it doesn't rain, the chance you either bring an umbrella or not. Well, umbrella, if it's not raining, was 1/5. So I'm going to write that as 0.2. So not taking an umbrella is 0.8. Okay, get in the habit of timing them straight away. So 0.09. That's it rains and I bring an umbrella. 0.01 is that it rains and I don't bring an umbrella. 0.18 is that it's not raining and I take an umbrella. And 0.72 is that it's not raining and I don't take an umbrella. So again, you can check that all those add up to 1. What is the probability that I take my umbrella? Well, this route has an umbrella and this option has an umbrella. So the probability of an umbrella is 0.09 at 0.18, so 0.27. B, if you see me with an umbrella, what is the probability it was raining that morning? So that's saying what's the probability that it's raining, given that you see me with an umbrella? Well, you know that I have an umbrella, so I'm going to write the options for an umbrella on the bottom. So that was 0.27, so that comes from the 0.09 and 0.18, the two that are highlighted. So out of those two options, which one was it where it was raining that morning? It was the first option, so that was a 0.09. So you can work that out and you just get a third. Yeah, so that seems to happen a lot in questions. They like giving you where they ask you to do one thing and then ask you to use that to do a conditional probability after it. If you're not too keen on doing conditional probabilities with tree diagrams, you can always draw a rain. So rain and umbrella, because you've got all the numbers from the tree diagram now, look. So I've got the middle is 0.09. I've got rain and not umbrella is 0.01. I've got umbrella and not rain is 0.18. and neither is that. So using the method before, given that you see me with an umbrella, that means I'm looking at this circle. Which of those did it rain? Well, it was 0.09. So it's 0.09 out of 0.09 plus 0.18, which gives us that third. Okay, let's look at an exam question. So the events A and B are independent, and I know that probability of A is 1/4, and the probability of A or B is 2/3. And it says find the probability of B and find the probability of not A and B. Okay, well, let's have a go at thinking about this one and think, right, well, you can decide on any diagram you want, I guess. So let's say we wanted to do, let's say Venn first of all. So I've got A and B. I don't know the middle, so I'm just going to put X. And I know that A is a quarter, so this must be quarter minus X. I don't know what B is at all. I know that A or B is 2/3. So that whole circle there, the whole of the two circles must be 2/3. So this bit here, which I'm going to put the blue dot, must be 2/3, take away everything that's there. So it's 2/3, take away quarter minus X, take away X, which if I work that out, I get 5/12. And if all of that adds up to 2/3, then that means the outside bit must be 1/3. Okay, this time I can't use the trick of adding everything up to give me 1 because the x's will cancel out naturally anyway. So we need to be a bit more clever this time and think, how else can I do it? So I must be given one more bit of information. And I'm given that the events are independent. So therefore, since they're independent, probability of A and B must equal probability of A times probability of B. So A and B was X, probability of A was a quarter, and probability of B is X at 5/12. So let's times both sides by 4 to get the quarter. So 4x equals X at 5/12. Take away X from both sides, so 3x equals 5/12. And divide both sides by 3, so X is 5/36. So I can fill that in the diagram now. So this is 5/36 in the middle, and a quarter take away that is 1/9. Okay, so now I can answer the question. Find the probability of B. Well, B is 5/36 at 5/12, which gives us 5/9. And find the probability of not A and B, which was 5/12, which is just the bit in the B circle that doesn't have A in it. Okay, if you want another way of thinking about this one, let's see if we've got any more space on this page. Yep. You could think of this as a tree diagram. So I have A and not A, B and not B, B and not B. So I start with A because I know what the probability is for A, so it's a quarter and 3/4. Now the only other thing I know is A or B is 2/3. So that's the first 3 options, gives me 2/3. So these 3 here should make 3/3. So this final option should make 1/3. So to get this branch, I would do 1/3 take away, 1/3 divided by 3/4, which gives me 4/5. So I'll rub that out. So that means this bit would be 5/9. And since they're independent, that means B doesn't depend on A, so the top branches will be the same as well. So 5/9, 4/9. Because B doesn't change whether A is happening or not, so the probabilities are the same. So if I wanted what's the probability of B, well, I've got straight away, it's 5/9, it's the same. Or I could do this branch and this branch. And what's the probability of not A and B? Well, it's 3/4 times 5/9. And if you times them together, you get 5/12. So see which one you're happier using, the Venn diagram or tree diagram. Okay, and finally, a bit of modeling with probability. So this is where we have to make assumptions. So a bag contains 12 blue counters and 9 yellow counters. 2 counters are picked at random without replacement. Find the probability that both counters are blue. Well, let's draw a tree for that one. That's the best way of doing it. So I can either draw a blue counter or a yellow counter. They're my only two options. Blue was 12 out of, altogether, 12 add 9 is 21. And yellow was 9 out of 21. If I took a blue one, then there's only 11 blues left out of 20 counters altogether, but there's still 9 yellows out of 20. Whereas if I take a yellow, there's still all 12 blues left out of 20, but there's only 8 yellows left now out of 20, blue and yellow. So again, times them together to get the end bit straight away. So 12 over 20. So if you work these out, at the end I'll get 11 over 35. So that's getting 2 blues. That's getting a blue and a yellow. That's getting a blue, a yellow and a blue. And that's getting 2 yellows. Okay, so now let's look at the questions. Find the probability that both counters are blue. So probability of blue and blue. That was 11 out of 35. Identify one assumption you made in your calculation. Is this assumption justified? Well, the assumption we're making is they're all equally likely to be picked. So that means are they the same shape, the same size? If the blue ones were a lot bigger than the yellow ones, it might be easier to pick a blue one, for example. So since it just says counters, that's kind of justified. You'd expect counters to be the same size. If the blue counters were slightly larger than the yellow ones, how would that change the answer to part A? Well, if they're larger, then you're more likely to pick them. So therefore, the answer to A will increase. So more likely to get 2 blues. So the probability would increase. And last page. A simple weather model assumes that the probability that it rains on any given day is 1/5, independently of any other day. So each day is like a new day, it doesn't depend on the other one. Find the probability it rains on 2 consecutive days. Well, I could draw a tree diagram, but just to save time, the probability of rains on the first day would be 1/5. Probability of rains on the day after would still be 1/5. Times them together, we just get 1/25. Comment on the suitability of the 2 assumptions made in the model. Well, the first one, the probability that it rains is 1/5. Well, it's not a fixed probability of it raining. It's not the same. If it rains, it's not the same probability. And that's independent. It's not independent. If it rains one day, it's maybe a bit less likely to rain the next day because there's less rain in the clouds. Whereas if it hasn't rained for a few days, it might be more likely to rain the following day. In an improved model, the probability that it rains in the first day is still 1/5, but the probability that it rains in the second day is 1/2 if it rained on the first day, and Q if it didn't. Okay, is the probability that it rains on 2 consecutive days larger or smaller than the first model? Well, let's have a go at drawing a tree for this one. So on the first day, let's say rain and not rain. So rain is 1/5, not rain is 4/5. And the second day, rain and not rain. Well, if it's rained, the probability it rains on the second day is 1/2. So the probability it doesn't rain is 1/2. And it was Q and not Q, so 1 minus Q. Yeah, what's the probability it rains on 2 consecutive days? So that's 1/5 times 1/2, which is 1/10, which is bigger than 1/25. So it's more likely to rain on 2 consecutive days. And the second one, the probability that it rains on the second day is still 1/5. Find the value of Q. Okay, well, if I get rid of this for a second, then we can fill in the in bits by timesing them. So I get 1/10, 1/10, I get 4Q/5, and 4 minus 4Q/5, just by timesing them together. And it says the probability of rains in the second day is still 1/5. So which roots give me 1/5? Well, this root it rains in the second day, and this root it rains in the second day. So these two together should give me 1/5. So I have an equation: 1/10 plus 4Q/5 equals 1/5. Now, if I times all that by 10 to get rid of the fractions, I get 1 plus 8Q equals 2. So 8Q must equal 1. So Q is 1/8. So it all comes down to the same skills. Making the diagram, you work out all the probabilities that you need, and answer the question based on that diagram. So make sure you practice lots of questions on this, because it's not the math skill that's the tricky part. The trickiest part of probability is interpreting the question. So keep going through it and make lots of notes. So lots of words that you're not sure of, make sure you ask, make sure you make a note of, so next time you know what it means.